Okay, so welcome back to the second lecture of Accelerating into the Future. If you get through the third lecture, I do promise stickers for everyone. So last time we motivated a bit about why we care about accelerators and why it's important to explore nature directly other than just indirectly or through precision experiments. And one thing that I didn't get a chance to talk about, and I have no chance to do it during this short amount of time, is the other important part of accelerators in particle physics is that they are multi-purpose facilities. It's not just kind of a monopurpose, I want to measure just an EDM. You can do thousands of experiments within the same facility. I just want you to keep that in mind. When you think of accelerators, really you should think of like telescopes, like JWST or Hubble. Now, we had left off with the fact that accelerator parameters are more important than just energy and luminosity, where that's typically what we restrict ourselves to as particle physicists. And the example we gave to this, that's nice and wet, was we don't just care about the integrated luminosity of how many events we see, we also care about the instantaneous luminosity because that really sets the scope for our experiment. And so the estimate we did last time was that the instantaneous luminosity at the LHC was 10 to the 34 centimeters squared per second. And with this instantaneous luminosity, and we said we wanted the integrated luminosity to be 3 inverse attobarns, we came up with a figure that to accomplish this takes around order 10 to the 8th seconds or 10 years. So that's where we had left off in explaining why the LHC is this 30-plus year program to accumulate this much data. Now, if we want to increase the energy, we want to probe nature at a shorter distance. We said any S-channel process, it doesn't care about the model you're doing. Just quantum mechanically, the amplitude tells you that the S-channel process dies like 1 over the center of mass energy squared. So naively, if you were able to build a powerful collider up to arbitrary energies up to the Planck scale, the problem is that you also want your luminosity to scale as the center of mass energy squared. Okay? So this is a fundamental problem, and the question is, even if you could accelerate particles to higher energy, can you keep scaling with the number of particles, the flux of particles that you can collide? Now, as particle theorists, we're always obsessed with energy, but I also want to point out that luminosity is showing up in many other places, not just the highest energies, and why we have to have this scaling. So for example, as I'm sure Yuri Zupan will talk about for precision physics, one of the standard things we do also in particle physics to test our models is to look at precision flavor physics. Okay? And unfortunately, we can't get lots of heavy flavor particles without particle accelerators. So for instance, one of the classic applications are so-called B factories. Okay. So these are done by taking an E plus E minus collider, tuning it to the resonance, for instance, the epsilon 4s, and this decays into B mesons. And if you have enough B mesons produced, then you can have enough statistics to start doing precision flavor physics and CKM. But just to give you an idea about this, so we said for high energies we have to scale the luminosity because the S-channel process is dying. But here, all it matters is how many particles can we produce. The cross-section doesn't change when I go from Clio at Cornell to Babar at SLAC to KEK and Bell in Japan. The cross-section is always of order nanobarn cross-sections for B physics. So therefore, the only chance to actually do precision measurements better is to increase the luminosity. So to give you an idea of scales, so the previous B factories, there were 2 experiments, Bell and Babar. And now there's currently a super B factory called Bell 2. And to give you an idea of what this does, this had roughly an inverse Autobarn of integrated luminosity at Bell. And so using a nanobarn cross-section, this is, we can call this a giga B factory. Okay? You have order a billion Bs produced. Okay? Now, Bell 2 is supposed to eventually get 50 inverse Autobarns. Okay? And what this will give us is roughly we'll now have order 10 billion B mesons. Okay. But again, I want to stress, this has nothing to do with increasing the energy. You're always sitting on the same resonance in QCD. You just need to make more of these particles. So how you go from a B factory to a super B factory, what we have to do, instead of waiting for our grandkids to finish the experiment, you have to increase the luminosity by roughly an order of magnitude. Okay? So the LHC's rough order of magnitude for its instantaneous luminosity is 10 to the 34th inverse centimeter squared per second. Bell 2, the hope is to get roughly an instantaneous luminosity that's roughly 10 to the 35 inverse centimeters squared per second. Okay? Now, the problem is, can you do this? Bell 2 is a running experiment. It's not reaching that luminosity goal. So we don't know if we'll actually ever get there. But you notice that these are very different colliders. The LHC is a PP collider at super high energies. Bell is an E plus E minus collider. It's asymmetric, but it's roughly at center mass energy about 10 GeV instead of 14 TeV. And you have similar luminosities. Okay? So there's not some magic that we have that we're actually able to dial luminosities to arbitrarily high energies. So we need to understand how are the actual limits of these luminosities and what are the tricks to improve it. Okay. So we're going to go through that. But first off, before we get into luminosity, energy is the thing everybody's interested in. So I want to emphasize, though, how if we could magically scale energies to higher and higher levels, it's not just an input to our colliders and our amplitudes that we want to calculate as theorists. Okay? The thing that you have to start getting in your mind is we think in high energy particle physics that we're kind of factorized. We're theorists, we're above everything. Experimentalists are the ones that do all the actual work, and accelerator physicists build the machine and then hand it off to us. Okay? These communities very rarely talk to each other except for maybe theory and experiment if you're in Pheno. But the point is that as we think about accelerating into the future, we need to realize that these are more and more coupled. Okay? So to give you a very coarse version of this, for instance, if we'd like to understand the highest energy colliders, okay? So what I'll do is give you the simplistic picture of what a collider looks like. So we'd like to measure charged particles, their momentum, and we'd like to capture the energy of the particles. So we have our little beam that's coming through this board, and then typically the configuration is you surround this by a tracker. Okay? You surround this by something to capture the energy of both charged and neutral particles, which you call a calorimeter. And then for particles that get all the way through, we have something like a muon system outside, and then you put a magnet to bend particles that are charged, somewhere inside or somewhere out. Of course, it's a little bit more complicated. You get something that looks like that, but this essentially does it for you. But now let's think about this just from the purely theory level of if I had a higher and higher energy collider, what does it do to us? So the two things we want to do are to measure the momentum of tracks in their tracker by bending them with the magnetic field, and we want to capture the energy with the calorimeter. So if I keep increasing the energy of my colliders and going to higher and higher energy, well, I've got two problems. I have higher energy deposition. So what happens is this makes it harder to contain Now, what I can do, of course, is keep scaling my detectors bigger and bigger, but if any of you have seen this, I mean, this is roughly the size of this physics building, okay? So that's 10 TeV. If I want to go another order of magnitude or two, now I got real issues with this. The other side of this is if I want to measure the momentum of charged particles, okay? If now instead of having TeV particles coming out, I have 10 TeV particles coming out, these things in the same magnetic field are going to become straighter and straighter and straighter. And how I actually get the momentum is I measure the curvature of these tracks. So momentum measurements become very hard. Okay. So all these things are interrelated. And the thing we'll talk about in the last lecture is also, depending on the types of particles we're using, there can be more backgrounds and detector constraints. And this general concept hasn't been needed as much for the LHC because it's been the only machine in town. But this comes under the general concept of machine detector interface, or MDI. So I'll talk about this a little bit more in the last lecture, but I want to make sure you just keep this in your mind that we can't factorize our thinking in terms of theory, experiment, and accelerator. These things are all going to be more and more coupled as your careers evolve and as we hope to get to these highest energies. So now we have to kind of go back to some of the nitty-gritties. And to do this, what I want to do is start off with talking about how we get to the highest energies. Yeah, maybe I'll switch there if the board's dry. Okay. So the hope is, by giving you a little bit of knowledge of where accelerator technology came from, where it's going, this will set the stage for what we're planning in the future, and it'll give you some idea of where the work is needed, or even where theorists can get involved in this. I mean, there are actually theorists that do accelerator physics as well. So let's start off with a very short lecture today on accelerator physics 101. Okay, this is kind of ironic that a theorist is giving this to you. So I'm going to have to go through a rapid tour through accelerator physics. But what I recommend to you is that just like there's the TASI school for theory, there is a really great school called the US Particle Accelerator School that's held every year or multiple times a year. If you search for USPAS, you'll find many lectures, videos, etc. So if you're interested in any of the things I'm talking about, you can go into a lot more detail there. And I will put up some lecture notes from this school on specific topics like plasma wake field and muon colliders at the end of this. Okay, so accelerator physics 101. If we want to get to something to higher energy, we have to take a particle that we know about, and it's roughly stable so that we can play around with it. And we need to act with a force. Stable-ish particle. Okay. And that's, of course, because if we're just looking for decays, like how the beginnings of the Standard Model were brought up, we only have the EV or KEV scale available to us through decays. Okay? So we have to do something that actually applies a force. Now, we have several forces available to us. Okay? Gravity, of course, is way too weak to do this. The strong force and the weak force, unfortunately, are way too short range to be of any use to us. So it turns out the only thing useful for accelerator physics is electromagnetism. It's the winner. Now, the nice thing about this is, as graduate students, you can go one of two ways. Okay? Everybody's gone through some Grad E&M course, Jackson, or some version of something like this. And so the way you can look about the rest of this lecture is that if you love Jackson, you should have been an accelerator physicist. On the other hand, if you hated Jackson, which maybe I'll officially admit to, then even though you might not have liked electromagnetism as a grad student, it actually is the basis for all accelerator physics. So it actually gives you a point to love accelerator physics if you want to understand fundamental physics. Now, in this lecture, it turns out I'm not going to need too much of E&M. Next lecture, we'll get into a little bit more when we talk about stable orbits. But we can do a lot with just the Lorentz force law. Okay? So we have two options for acting on charged particles. We can act with an E or a B field. So we have our force is E V cross B plus our electric field. Okay? And as everyone remembers from back in the day in undergraduate E&M, if you take some particle moving from some position R1 to some position R2, and you ask, how does the particle's energy change as I'm influenced by electric and magnetic fields? Well, we just calculate the work on this of our Lorentz force law dotted into our path. So we have our E, R1, R2, and then we have our V cross B plus E dotted into dr. And then you all remember the famous consequence when you learn electromagnetism the first time, is that since our velocity vector is going to be proportional to the direction of our path, this vector, V cross B, will be orthogonal to it, so our magnetic field doesn't do any work on the particle. So therefore, this contribution vanishes. So the only way, E fields are the only thing that can accelerate particle energies. Okay. So from our perspective, if we want to go to higher energy, all you have to do is be a master of electric fields. Okay? Now, there is a subtlety, of course. There are some accelerators designed on the principle that if I have a changing magnetic field, of course, I can generate an E field. So you can kind of primarily have magnetic fields. But at the end of the day, we have to have an E field to accelerate. Okay? And so that's why all we really care about in terms of our energy gain for what is the shortest distances that we can access, we just care about the potential difference that a particle experiences, that a charged particle experiences. Okay? So our delta E is simply going to be E times U, our potential it experiences. So that's why when I talked about that list of discoveries in the Standard Model and how many of them were accelerator physics discoveries versus others, this actually was the original version of with Thomson's experiment, where the original accelerator was simply the cathode ray tube. All right? So you all remember the experiment you see in whether it was high school physics or college physics, where essentially you take a vacuum tube or something very close to a vacuum, you have some cathode and some potential that you put on here, and you have an anode sitting over here, and you heat this up, you generate your rays, you have a potential difference across here, you put a little hole inside your anode, the particles zip right through, and out they come accelerating. Okay? That's the old school version of a particle accelerator. And although I said there are 30,000 particle accelerators, if we kind of went back order 20 years or so, there was a lot more particle accelerators. Your old TV that your parents had, or maybe when you're 5 years old or something, I mean, you're all so young, every television had a particle accelerator inside of it. You had this heater to get thermiotic emission of electrons. You had your cathode and your anode. Particles pass here. They get bent by a magnetic field. They hit the screen. You get the picture. Okay? Now, amazingly, TVs of old had all this technology, right? Because I'm sure you've also heard that in this static, when you have an old antenna TV, there's a little bit of the CMB that you're picking up there too. So maybe it's a sad thing we're miniaturizing everything and losing this connection to what the basic physics was. But I still don't want one of those on my desk any longer. Okay. So particle accelerators are essentially a very easy concept. We can put them in all different types of things. All we need to do is have a charged particle that's relatively stable, get an E field to accelerate it, maybe steer it with some B fields like in a television, and then take whatever path you want, smash it into something, or smash it into another particle, and you're done. Okay? So particle accelerators are so easy, then they even get kind of viewed in terms of movies. Okay, this is maybe too young for you, but remember back to Iron Man 2, you just build a particle accelerator in your basement, and you're done. Okay. So the question is, okay, this is a little dark to see Robert Downey Jr., I guess, but why doesn't the LHC look like this? I mean, it's a circle. It kind of looks like the LHC. But what is the technology that says you can't put this in your basement, and you have to build this 27-kilometer ring? So if we go back to this cathode ray tube example of just having some cathode and anode, some potential difference across this, well, what's really stopping you is only what is the maximum potential that you can get. That's the only thing stopping you. Okay? That gives you your energy that you gain. Now, if we think about this, the problem is, as theorists, we can always say, oh, well, just give me a TeV potential a teravolt potential difference, and I can get a teravolt energy that comes out. But if we take an electrostatic accelerator, which is what a cathode ray tube is, so I'm not changing the E field at all. Well, the problem is, no matter how well you build this technology, okay, it's never going to be exactly as a theorist designs it in terms of just having a potential difference, right? If you have an insulator, like a vacuum in here, no matter how good a vacuum you think there is always some resistivity that's not exactly putting you to say that this is infinite resistance. So if we think about the current that goes through when I put a potential difference across my cathode to my anode, I'll have some current that's generated by the potential difference. So here's my potential versus my current. And so the fact that it's not an ideal resistor, an ideal insulator, means I'll have some ohmic part that'll always generate some current because I have a potential across it. Now, there's also the fact that I have ions that are living in here. I can't get an exact vacuum inside of here. So there will also be some ion current that we can also view as the beam current that's going through here. Okay? And that'll essentially saturate as I increase my potential difference because the ions will get pushed off, and then I'll just be left with the beam current that goes through. But the problem is, as I keep increasing my potential difference across this, as I look at the electrodes that are generating my electron beam that's coming out of this, as I increase the potential more and more and more, eventually I get a cascading effect where the potential is so high that I'm going to essentially be bubbling off more and more electrons, running into ions, and I get something called a corona discharge. Essentially, the thing sparks, and the entire thing discharges, so I don't have this large potential difference anymore. Yeah?
Should there be that we reflect with like a spike in the current at some...
Well, yeah, that's the curve I haven't drawn yet. Okay. So the last one is you don't see it, and then all of a sudden you see what we call corona discharge. And what essentially this does is that even though electrostatic accelerators are a nice concept, it limits to some maximum potential that we can generate with an electrostatic device. And so, for example, when we have this spark discharge in a cathode ray tube, we roughly get the Umax is, let's call it, a few megavolts. Okay? So if we have an electric charge of E, we can get to MeV energies with this.
Shouldn't this max be per distance?
No, this is in terms of just what the potential is. I'm not talking about the gradient yet. That's the E field. This is just the potential. We'll talk about the gradient as well. So clearly, just using your television from back in the day, you're not going to get to the Planck scale. You're going to be stuck at like the MeV scale at most. So we need to somehow develop some technology that can push us beyond this simple electrostatic generation. And there are essentially two ways to do electrostatic generators that go beyond this megavolt potential where it starts to break down. So the first example is the so-called Cockcroft-Walton generator. And the idea is that it's very hard to make an absolute potential difference across these things in terms of my cathode and anode. So essentially, what you do is design a clever generator where you use some AC input for your voltage, so it's going plus and minus, but you generate a circuit with diodes so that even though you have both the plus and minus voltage, you only actually charge capacitors for the positive field. So essentially, you kind of keep increasing. You get a U, then you get a 2U, then you get a 4U, et cetera, with the circuit diagram. And this is the circuit diagram, if you remember back from your undergraduate days, unless you had to do some grad lab with circuits. But you kind of see it actually in the actual Cockcroft-Waltons that they're generating here. Okay? Now, the idea behind Cockcroft-Walton generators is that in principle, you can get some maximum potential that's equal to 2n, the number of these circuit layers, times your voltage that you come in with your AC voltage. Okay, so in principle, you can keep generating at a higher and higher voltage. But again, even though this is a different way to generate a higher voltage, you're still going to be limited by the breakdown effect. You're going to have discharge eventually. That even if you get a big potential, now you want to put that potential onto a particle. You want to have some acceleration to that potential. And so it turns off that these Cockcroft-Walton generators, even though they're the first step beyond the cathode ray tubes, these also give you a Umax that's order a megavolt, okay? Because the breakdown effects happen in the same way. So there's one other electrostatic generator, and it's also in use still. And this is the one you've probably all seen as an undergraduate. This is the Van de Graaff generator, okay? So instead of using an AC source, you're just physically transferring the charge, and then you're actually using corona discharge to actually generate your potential for your accelerator that you're going to do. Okay? Now, this one is nice because you can play the game of showing how sparks come off of this to undergrads when you're TAing, or maybe your high school physics teacher did this. But unfortunately, it's still not going to give you something that's parametrically different from this megavolt scale. Okay? Now, you can do clever things when you have sort of megavolt potentials. You can maybe double it. So an example of if I take one of these Van de Graaff generators, so this is creating a very large potential difference. And you can create something that's actually used well over the world. They're called tandem accelerators. And this is a way to 2x your potential. And the basic idea is, let's say you wanted to accelerate protons that had a positive charge, or electrons with a negative charge. You take your ions, okay? And what you do is if you had a positive ion to start, you first put it through some charge exchange, basically a region where you can add electrons on there. And let's say you take something that's an ion that starts off with positive charge, and then you give it some electrons, you turn it into an ion with negative charge. Then you take a Van de Graaff generator that gives you this large potential difference, and you essentially set up an accelerating region where your Van de Graaff is sitting here, and you give it a potential at this point. So you accelerate your negatively charged particles up to this potential. You pull them in with a positive potential here. And then what you do is you add a clever trick, which we call an electron stripper, where you essentially pass your negatively charged ions through a gas to knock off the extra electrons you had to turn into a positively charged ion. And now you have your ion going back the other direction, back down the potential. That's now back to I plus again. You have I minus here and I plus here. Okay? And these are actually used. This is an example of a Van de Graaff tandem accelerator that was sitting in the basement of Stony Brook until about 2011. Remnants of it still exist because we have to do something else. But these are used kind of as a first step to getting megavolt potentials that you can accelerate through. Now, the problem is you can actually get a little bit more than a megavolt. Okay, I'm just always saying megavolt is the rough scale for this. Van de Graaff generators, if you use these tandem Van de Graaff generators and you put an inert gas that's pressurized in this, you can actually increase the breakdown voltage, so you can get higher. And Van de Graaff generators can get you roughly up to a Umax, let's call it 20 megavolts, okay, in that neighborhood. Of course, they become very large structures, and no matter what we're doing, there's no really way to go beyond this. Now, the question that was brought up is, beyond just what is the total breakdown voltage, what is the actual gradient that I get for these acceleration fields? Okay, so you notice that this is a very large thing, roughly in terms of a person size. Now, the breakdown voltage that occurs for any of these electrostatic generators, essentially the max gradient that you get out of any electrostatic accelerator is about 3 megavolts per meter. Okay? Now, we haven't talked about high energies at all so far. We're just kind of going from the bottom up. But now let's go back and put our hat on of saying, hey, I'd like to accelerate to the LHC energies or beyond. Okay? So if we said we'd like to have a particle where my energy of my beam was really a TeV, okay? That's just getting into today's technology, not the future. Well, unfortunately, with a gradient of order of megavolt per meter, now we have to have an accelerator length that's going to be of order 1,000 kilometers. Okay? Now, it kind of sounds abstract in terms of, okay, 1,000 kilometers, no big deal. But now, let's put this on the map. So if going from Boulder, we would need to make a linear accelerator that was roughly to here, okay? If we could repeat this electrostatic structure over and over again, okay? So clearly, electrostatic accelerators are not the path to high energies. They are very useful. As I said, there's over 30,000 particle accelerators in the world. You don't need to get to a TeV to make shrimp wrap. You don't need to get to a TeV to do some X-ray medical scan, okay? So these accelerators are used all over the place, and secretly, when I'll come back at the end of this class to the LHC, they're used in part at the LHC, but unfortunately, they're just not the right thing to scale up to get our Umax large enough. So regardless of, even if I could build this thing, I'm not actually going to build just one thing that has this TeV potential. As I said, this gradient tells me I would have to build an electrostatic accelerator, and I have to build it over and over and over again to get to these energies. So I would like to somehow repeat my acceleration mechanism or have some super large gradient. So we'll go the two different directions for that. And so what that is going to lead us to is what turns out to be the backbone of all modern high energy accelerators. And that's the concept of RF acceleration. Okay. So the problem with electrostatic accelerators is the fact that it's all based on the potential I want to get to. Okay? If I can't get a big enough potential because of the breakdown of my field, then I'm just out of luck. Now, with RF acceleration, the idea is it's actually very economical to make power sources that have an RF power source. Okay? We have them all around in terms of radio, radar, where these things were invented before. And so we can always come up with a power source that has a frequency and a potential. So we have our potential that varies. We have some Umax, and we have some frequency, omega t, that it's varying with. Okay? Now, why are these things good to start with? As I said, they've been around forever, and they're around in every possible technology you see. And just like going to the cathode ray tube, we'll go to your microwave. Okay? These still exist, unlike the CRT TVs. So microwaves are an RF power source. And what microwaves are generated by is you typically have a magnetron inside of it. And the basic idea is you have something like your electrostatic generator in terms of your cathode and your anode. You are generating your electrons. You have a magnet which makes them orbit, okay? And the point is, unlike the electrostatic where you just had a very simple anode, you design your anode in a very particular way so that you have these cavities that give you resonances in the microwave frequency region, and then eventually you read out these electromagnetic waves that are of order microwaves. So these things are cheap, they're all over the place, but they're not a particle accelerator, right? So a microwave has an RF power source. The electromagnetic wave is going to shake all of your molecules. So what's the only difference between a microwave and a particle accelerator? It's how you design essentially the cavity that these electromagnetic waves are powering, okay? So what do we have to do? So instead of just jiggling up and down like a microwave, we essentially have to think of this kind of like the Cockcroft-Walton, where we were only wanting to keep the positive parts of it. Okay, we were charging the capacitors. So this idea for how to generate RF acceleration rather than just microwave heating, this goes back to icing, and since these are theorists, this is not that icing. There are multiple icings in the history of physics. And the first accelerator was done by Witherow about 3 years after the idea came out. Okay. So we want to come up with some sort of technology that would only let us see the positive parts of the potential of our RF source. So the clever idea, and I'll give the picture rather than drawing this one, is essentially we're going to use drift tubes. Okay, we're going to use some conducting surface to act as a Faraday cage. So we'll have some source of charged particles we want to accelerate. We'll couple these conducting surfaces to some RF power source, which is going plus and minus all the time. But we'll try to arrange this such that when the particle travels through one of them where there's no field inside, that's when the potential is negative. And then when I get here, the potential will be positive, and I'll get accelerated. Then I'll hit here, it'll be negative, positive, and so on. Okay? So this is the concept of a linear RF accelerator that's been around for the better part of a century. And in principle, what it allows us to do is if I think of going through all these drift tubes, then after the kth drift tube, what will I have? Well, if I'm only seeing the positive parts of the potential, I'll always see the same Umax times the sine of the phase that I see. So I'll have that the energy of my particle will be up to K times Q Umax. Okay, so the potential times the charge. And then what is the actual phase of my electromagnetic wave that I see? Okay, so this is the average phase that I see in these drift regions here. Okay. So it's a clever way because in this accelerator, what I'm not doing is I'm not trying to maximize what my potential is. I can keep my potential at a reasonable level where I don't have a discharge. I just get to multiply it by this integer k, which is how many segments of the accelerator I go through. Okay. So it's kind of a clever way to try to get around this breakdown or charge-discharge. Now, if I take this expression and say, let me start with a particle that's at rest for my ion source. So at the beginning, it'll be a non-relativistic particle. And if it's, for instance, a proton, it'll be a while before it's relativistic. So if this is my energy after the kth part that I go through, if it's non-relativistic, I can say, well, my energy will just be given by the kinetic energy of this particle, non-relativistic. And so the thing that I have to do, though, which is the hard part of it, which is why it's not exactly trivial, is as I'm accelerating through here, okay, the velocity of the particle will keep changing. So if I want to keep matching to only see the positive part of the potential, I have to keep adjusting my structure of my drift tubes so that the gap is synchronized with what the field's frequency is. Okay? So if I think of how large these drift regions have to be, the given drift region, okay, it has to be exactly half of the period of my RF. Okay, so I see only the positive side of this. So if my drift has to be exactly given by the period, the RF, so we can write this as VK tau RF over 2. Okay? So what this tells us is that if my velocity keeps changing because I keep accelerating, I'm going to have to keep spacing out the drift tubes to do this. Now, in principle, I wouldn't have to if I keep changing the RF frequency. I could keep this smaller. But the problem here is that, as you see here, I am having to couple this to some power source. Okay? And if I don't want the cost to blow up exponentially on me of having every single drift tube being connected to a different RF source with a different frequency, then if I couple to the same RF source, which has the same frequency, I just have to adjust the geometry of my accelerator as I go on. But the nice thing is, if I think about this, this is the non-relativistic version of this. And if I replace what my LK looks like in terms of my frequency and my wavelength, this looks like beta lambda RF over 2. Okay? So if I have beta approximately 1, the nice thing is once I get to a relativistic particle, then my drift lengths don't have to change. Okay? The energy of my particle will keep increasing, but relativity saves me and I don't have to keep making this infinitely long. Okay? So what I get here then for a non-relativistic version of this is that my drift tube length will look like 1 over the RF frequency and the square root of k q u max sine of my phase over 2m. Okay? So what we see here, though, is we have a rough scaling that at the beginning of acceleration, my length has to increase roughly with the square root of the number of stages that I'm going through. Okay? So it gets long pretty quickly in terms of you put in numbers. Now, as I said, luckily you're saved by the relativistic effects. But an absolutely crucial part of this, the entire story, only works because I keep changing the length so I only hit the positive part of the potential. Okay. Now, the problem is if I want to have some very large acceleration, right? Let's say we put in a U max that's typical of the electrostatic generators of order of megavolt or something like that. If I want to get to a TeV or hundreds of GeV or 10 GeV, then I need many, many stages here. Okay? Now, what this means is each one of these things, as I couple to these drift tubes, okay, I could have slight variations in the potential, right? I mean, I would have to machine this exactly so that my particle is traveling this ideal trajectory as a theorist would imagine. So the problem is, if I have slightly different Umaxes that I'm going through, or slightly different phases that I'm going through, I think I'm accelerating in this very clever way, but now all of a sudden the beam goes off, I mismatch, and I don't accelerate at all. Okay. So what I have to do, and the clever trick that works for RF acceleration, is the idea of phase focusing. Sure, I'll do it right now. So we want to try to make sure that all of my particles accelerate together and they don't just suddenly like stop and hit the wall or something like that. So the concept, as I said, is called phase focusing. And the idea is we have this potential, that's U max sine omega t. And naively, what we'd like to do is have our phase be such that I hit the maximum potential. I want to have my sine be 1 here. Okay? So we can think of this in terms of the phase that I'm seeing, sine psi 0. this thing would have, for instance, pi over 2. That would be the maximum acceleration I can get. The problem, though, is I'm sitting exactly at pi over 2, then any disruption in this, I go one way or the other way. So the clever solution is not to choose pi over 2, to choose some delta psi such that I'm slightly less than pi over 2. Okay. And then what we can do is think of this in terms of our potential as a function of time. Okay, and we'll have, put a 0 here. So this would be sitting at pi over 2 if this was the phase everything saw in terms of my acceleration. But what we'll choose is actually slightly below it. Okay, so we have a u max here, and then we'll have a u effective that we'll choose here. Okay. Now, of course, since I'm not sitting at pi over 2, what the phase I'll see is I'll see a phase slightly less than it. And what that means is I'm getting this on average, but now I have two choices. If a particle can pick up a little more energy or a little less energy, kind of thinking about the perturbations around what I want to be. So let's say, for instance, this is my average phase that I'm trying to hit, and I have a particle that happened to get a little bit more energy than planned. Okay? So it goes through here. If it has a little bit more energy than planned, what is it doing? That means it's going faster than I expected. So what it means is that I will hit the next cavity a little bit early. Okay? So I had too much energy, but now I'll have a little too less energy. So I'll naturally slow down to what the design velocity going through. Similarly, if I have too little energy, if I get accelerated, then it takes a little longer than planned. Instead of hitting this, I'll actually hit this, and I'll pick up a little bit more energy. And then I'll naturally get back to where I'm supposed to be in terms of the nominal velocity. And so this concept is called phase focusing. And so then this u effective that I am going to actually have my particles see is going to be whatever my u max is times sine of this minus whatever offset of my phase. Okay. Now, this is kind of a clever way to say nobody can build an exactly perfect system. As theorists, we always write the equations for the ideal world and then have to go off of that. So this concept is a way to keep the particles together and all accelerating. What this also naturally does is that if I stick more than one particle through here, if I stick a bunch of particles, because I'd actually eventually like to get luminosity, what I'm going to do is I'm going to have essentially oscillations around this u max. Okay? So what happens is that my particles, if I'm sticking a bunch of particles through this, these particles will naturally bunch. Okay? Instead of being a continuous stream, they're going to bunch and oscillate around what the natural frequency of oscillations for my RF system is. So that's why, for instance, in particle physics, you often hear about like bunches of particles colliding together. Okay? That is a direct consequence of what is the acceleration mechanism. Yes, there are situations where we actually want to bunch particles together to get the maximum number of particles on a target or something like that, but it actually is an outcome of our basic concept of RF acceleration. Okay. Now, as I said, in the limit that we get relativistic, our beta is approximately 1. Okay, that equation disappeared. But the point is that these drift lengths become essentially constant for very high energy particles. So instead of thinking of these drift tubes that get longer and longer and longer, the distances are the same. And what you typically do after this early concept, and what you see, is that what I can switch to instead of just drift spaces is, since this thing is uniform in size for beta approximately 1, what I can do is what we use are RF cavities. Okay? So instead of having conductor, empty space where you get accelerated, conductor, empty space where you get accelerated, you all see the modern version of this, which every particle accelerator is based on in terms of an RF cavity structure. So these gaps here, okay, these are the drifts where I have the phase that I don't want, and these bubble parts here, they're designed so that they're resonant at the frequency in terms of my electric field that I want. Now, we can also see what's the natural size of these things. So this is an RF cavity for, it says here, LCS2. So this is the LINAC cavity light source, LINAC coherent light source, okay? And so for beta approximately of 1, my drift space needs to be beta lambda RF over 2. Okay, it says on there that this is a 1.3 gigahertz cavity. So my lambda RF is just going to be C over my RF frequency. And so we got 3 times 10 to the 8th over lambda RF. And my Li is roughly lambda RF over 2. So what we get here is this is roughly 15 centimeters for nu of order a gigahertz. Okay? So that's why these cavities look like what they do. Okay? If I'm driving something at a gigahertz or a few hundred megahertz, it'll be a little bit bigger in terms of order of magnitude, but this is roughly the human scale that we're seeing. Now the nice thing is, in principle, I can accelerate to as high of energy as I want. I just stack these RF cavities over and over and over again. Now the trade-off is, since this went like the number of structures times Umax, right? We didn't get the square root factor. We just got the number of cycles that I went through, okay? The trade-off is if my U that I can accelerate to looks like the number of structures times my Umax of these structures, what I'm essentially going to have is, if I'm stuck with the size of these things being not tiny, like tabletop or on a chip, these things are going to be very large if I can't get a much larger Umax. Okay. Vice versa, I could say, well, what if I could start putting a larger and larger Umax into the system and get a shorter acceleration, shorter cavities, so I could go to higher and higher frequencies for my RF power sources. Okay. The problem, though, is that no matter what I do, even though this is not an electrostatic accelerator anymore, I have a conducting surface that I'm putting a large potential across. I can't take my Umax arbitrarily large. Okay? Just like you have a spark discharge of your Van de Graaff generator, your cathode ray tube, eventually what happens is if you start putting more and more potential on this to try to make these structures shorter so you don't have to go to Kansas to make your accelerator, then what happens is that your RF cavities will break down too. And essentially what will happen is, as I put a big potential across here, I'll start to bubble electrons off the surface of this, and they'll fly across, smash on the other side, they'll damage the cavity, the whole thing goes to hell, and I don't have an accelerator anymore. So what sets this rough limit? So there is a little bit difference than the kind of megavolt scale that I gave last time. So when we talk about relativistic acceleration, and we're talking about these high frequencies that we want to use for this to make the cavity shorter, there's something that was empirically derived originally, and it's called the Kilpatrick limit. Yep.
So I see a problem with this geometry. I don't know if this is what you're about to talk about, but because the particle's being exposed to it isn't oscillating. It's not equal oppositely oscillating. It's still oscillating, and that means in its rest frame it's being vibrated. If it's being vibrated so that it will radiate, and the frequency in its rest frame will be very high for high energy, so eventually it will radiate so much you would lose all its power.
So we're going to talk about that, and that's called synchrotron radiation. We'll get to that. From the purposes of design here right now, I'm assuming that there's no energy loss, that the particle's energy is just being accelerated. But we will talk about that. It's a good point. So this Kilpatrick limit, though, this is just about the RF breakdown. This has nothing to do with the particle. This has to do with when the cavity can't support that potential any longer. And it turns out that the Kilpatrick limit for normal conducting and superconducting cavities gives you a gradient that is roughly between 30 to 100 megavolts per meter. Okay? So RF cavities are a great way where I don't have to have a large Umax. I can get a large acceleration if I keep stacking them one after the other. But unfortunately, there is a limit to technology right now in terms of how much what's the gradient of these accelerations that we can do. Now, the nice thing is, compared to the tandem accelerator and the Van de Graaff accelerator that I showed earlier, we said that was about 3 megavolts per meter, okay? And this depends roughly on what the frequency of these cavities are, and as I said, superconducting versus normal conducting. But what we see here is we've gained roughly an order of magnitude or more, okay? 1 to 2 orders of magnitude compared to electrostatic accelerators. Yep. So these all are vacuum inside. That's already an assumption, because if you have like a gas in it, then this discharge would happen a lot further. But it's a good question, yeah. Yeah, that's in vacuum, doing as much as you can to avoid this discharge. So this limit, we get roughly 1 to 2 orders of magnitude compared to electrostatic generators, which is why RF acceleration is used pretty much everywhere. Yep. Sure. Yeah, in the sense of like the entire thing, the entire structure has to keep being long. I don't know if my picture showed it very well here. Yeah, I mean, you kind of see the growth a little bit there, but yeah. You always have to basically tau, whatever the frequency, the period over 2 is how long you have to hit the same phase. So now what we can do, though, is we took the estimate to get to a TeV scale of acceleration from our electrostatic, and we said that was 1,000 kilometers. So if we just do a linear accelerator, a LINAC out of RF, what this means is to get to the TeV scale, since I can drop a couple orders of magnitude, if I take the favorable 100 megavolts per meter, this tells me I now have an order 10 kilometer accelerator. Now again, this is assuming that I don't have to do anything else, that I just stack RF cavity after RF cavity, I get only 10 kilometers. Yeah.
Is there an easy way to see like where this factor 10 improvement is coming from versus the electrostatic case?
As I said, this was originally empirically found. There's not kind of a fundamental understanding of where the breakdown is. This, one of the amusing things is, as we'd like to think this is all just electromagnetism and we could just in principle understand all these things from first principles, I'll give an anecdote where the current SRF cavities, which are a way to operate with lower power, and we'll talk about that later, the way they were found is to have a superconducting cavity, you want to bake this material, okay, and kind of go over and over again to make it superconducting and stay. One time at Fermilab, they took one of these RF cavities, they put it in an oven, and they forgot to close all of the valves, so some gas leaked in, and all of a sudden they found, oh my gosh, my accelerating gradient was essentially a factor of 2 larger. So this is at the level. So at the level of ideal things, we get rough schematics, but yeah, there's not a first principles derivation of this that I know of. Now, as I said, because you get this rough order of magnitude to 2, before you have breakdown, you can shrink it down. Now we'll come to, unfortunately, the last thing that we have to think about for any collider 2, which is cost, okay? So in principle, I could make a Planck scale accelerating gradient, okay? But length is proportional to cost, or vice versa, depending on which is your primary thing that you want to save. And so just to give you a scale, because I mean, these are things as theorists we never think about. I mean, our grants are so tiny, we don't have to ever care about big money. To give you a scale, it's roughly 60 to 600 million US dollars per kilometer to dig a tunnel, okay? 10 kilometers is roughly saturating what you're going to go and ask any politician for. Okay. So this gives you an idea, and then we'll come back to this. So RF LINACs, they're great. You can get large accelerations, but unfortunately, if you do it as a LINAC, they get longer and longer and longer, and eventually I run into a cost issue. I would love to build a collider from Boulder to Kansas City, but now we're talking the defense budget of the US per year, not just order $10 billion. That's just digging the tunnel. Yeah. That number is also conservative. If you include the Second Avenue subway in New York City, the number is roughly 2.5 billion per mile. But hopefully, at large scale, things become more efficient. So this is a great way. All acceleration in modern days are based on RF acceleration. But what we'd like to do then is somehow not have to build as big of a tunnel. And the other part, which we haven't talked about at all, is if I have to keep stacking these RF cavities over and over and over again, I have to build all these cavities, and I have to power all these cavities. Okay? So the power budget goes up, and the cost for making these go up. So the idea behind why RF acceleration was nice is that I could essentially reuse the same potential. Okay? I went through it multiple cycles. So what if there was a way to reuse the same accelerating mechanism, not have to linearly stack these over and over again? Okay? And that could potentially shrink the size of our accelerators. And that brings us to the famous cyclotron. Okay? So if instead of just making a line, I want to come back in a circle and do this over and over again. So thank you. So this was from Lawrence. There's the Oppenheimer version of Lawrence. And what's the idea behind the cyclotron? Okay? So the idea is I want to use the same principle as RF, where I have a potential that's oscillating, and I only want to see the positive side of the potential. And of course, this diagram I pulled off Wikipedia, so it's not the best version of this. But what the structure is I want to do something similar, where I have some RF power source that goes plus and minus, and I'll have two conducting regions that are called Ds because they look like a letter D. Okay? And when I go across this gap, I'll feel the accelerating field. In these two D regions, I won't feel the accelerating field. And then, to have this go in a circle, what I need to do is put a large dipole field across it, a constant dipole. Okay? So the idea is essentially the same as the RF cavity, in the sense I reuse my potential that's going up and down, but instead of stacking in a line, I go around in a circle over and over again. Now, what that turns out to mean is that now to go in a circle rather than a straight line, I have this magnetic force, okay, which will have a magnitude, which is just QVB. And if I think about what is the particle's motion for this trajectory, so I'm going around, I'll have a central force. So I'll have my QVB over mv squared r. I'll assume we're non-relativistic for a start. And what it tells us is that as I keep feeling this accelerating gap over and over again, my energy of the particle increased, so the velocity of the particle increased in the non-relativistic limit. And so therefore, my radius will keep increasing as mv over qb. Okay? And now the cool thing, and why the cyclotron was such a nice advance, is, okay, I know that my actual orbits are getting bigger and bigger, but the trick of the linear accelerator, the Wittero accelerator, and the RF cavities was I still have to match the frequency of power generation with when I'm seeing the right phase here. Okay? So if we say, what is the period of going around in this orbit? So the period will just be 2 pi r over the velocity. And so therefore, this will be 2 pi m over qb. So for the non-relativistic version of this, the period of going around this does not depend upon the velocity. Okay? If you give me a B field and what particle it is, your m and q, that you're accelerating, I just have a fixed frequency that's going around. So therefore, I can choose what is the RF frequency that I need to power this at, and I'll automatically synchronize. Instead of continually have to build the cavity bigger and bigger and bigger like we did before, it's an auto-synchronization. Okay? So all I have to do is choose the condition for my RF frequency that my period is a half of my RF frequency. Okay? Now, even though we have this automatic synchronization that we didn't have for the linear collider, we had to build it in this way, the problem is, if I have a cyclotron like this, the radius, as I said, is going to get bigger and bigger. Okay? So if I want to have an accelerator that looks like this with a constant B field across of it, the problem is, as the particle spirals out further and further and further, I have to make these Ds larger and larger and larger, and the actual size of the magnets larger and larger and larger. Okay? So eventually, I just reach a construction limit that my magnets become too large to ever build a reasonable cyclotron. Okay? So there are permutations on the cyclotron. And as I've said, this is the non-relativistic limit. You also have to take into account that essentially as you go faster and faster, the mass of this particle is getting heavier and heavier from this perspective. So you don't have this autosynchronization. And so you'll see things like things called the synchrocyclotron or the isocyclotron, or what's actually used. How many of you have heard of MUMMY, the experiment they use for dark photon? Okay, one. So the idea behind this is, as they go relativistic, different tricks to kind of keep the size smaller. So the synchrocyclotron is changing the RF frequency instead of keeping it fixed. The isocyclotron changed the B field. And the microtron basically says, let me use this sort of deconstruction and then have a linear accelerator in between here, and I just keep turning them around back and forth. Unfortunately, none of them scale very big, well, okay, because the magnetic fields can only get so large if I'm always just bending it once. So that brings us to the last thing, which is what all modern accelerators for high energy are other than LinX, and that is the synchrotron. Okay. So the problem is, in terms of this basic idea of the cyclotron, I either have to make the magnetic field bigger and bigger and bigger, which is hard to do, and the radius will eventually spiral out. So the question is, what if I keep R fixed? Okay. Now, this is perfectly fine. I just have to figure out what are the parameters that go into this. And what if I keep R fixed, use the same concept of R of acceleration? For relativistic particles, the R is given by the energy of the particle over EC times the magnetic field, if I was trying to keep this at the same fixed R. Okay? Now, what this means is that if you want an accelerator that doesn't spiral out in size and keeps a fixed size for all your orbits, as I raise the energy of my particles through acceleration through off cavities, I have to synchronously raise the magnetic field. Okay, that's where the name synchrotron comes from, that I have to keep these synchronized. Now, if I look at what this means is I can make an accelerator that combines these basic principles. If I put a particle into the path, I'll have some magnets that bend it to keep it at this radius. And I can put only one RF cavity. I don't have to put thousands of RF cavities. I can in principle just have one accelerating mechanism. And because I see it over and over and over, it goes through the same turn, I can keep making this larger and larger. Higher and higher energy. So a synchrotron is a way to get to very high energies using very few RF components and in a small package. Okay, the RF power will reduce. Now, of course, it doesn't have the auto synchronization. It has to satisfy this condition in terms of E and B. And furthermore, if I want to see, if I had just one RF element here, okay, I have to build my accelerating path such that I satisfy that if I have, it has to be a multiple of my RF frequency, right? So if I'm using order 100 megahertz to gigahertz cavities, but yet the entire thing is 27 kilometers like the LHC, I better build that thing dang accurate to get right on that in terms of I'm not going to see the wrong phase, okay? Nevertheless, it is possible, and the point is that once you build such a machine, you're just given that the energy increase will be the same formula that we have, where you'll get this much per turn. Okay? So if you have a stable particle, you just keep going like this over and over and over again. The only thing that will set the dimensions of this, in terms of you could in principle get arbitrarily high energies, is what is the maximum magnetic field you want. If you tell me the fixed radius, depending on how high of energy you get, there's a maximum magnetic field I can achieve. Okay? Just to give you an idea for what the kind of scales of these things are, and in principle, when I separate the acceleration and the bending into two different functions as I go around this ring, I could also have the bending come from electric fields, right? There's no reason it has to be from magnetic fields. But just to give you some scales, if I have a B field of 1 Tesla, and I ask for what's the same force that I need from an electric field, so the force for a relativistic particle, so this is CB, and this is equivalent to an electric field that's about 300 megavolts per meter. Okay? So as I already said, the maximum gradients we get out of electric structures are roughly 100 megavolts per meter. So this is why synchrotrons always have B elements, not all E elements for high energies, because otherwise you can get Tesla fields easily. 300 megavolts per meter is a gradient that's almost impossible. And to give you a scale for actual particle accelerators, the LHC, its bending magnets are 8.33 Tesla. Okay? So B maximum is 8.33 Tesla. And so you're definitely orders of magnitude above what you could do with electric components.
This 300 megavolts per meter, that's similar to the limit for the RF cavity. That means that you could get about 1 Tesla of lateral acceleration if you just introduce an extra polarization in the cavity, it would seem.
Yeah, I mean, you can use an RF cavity. I mean, anytime you can use an electric field, you can bend it like that. The question also is then you're kind of doing it in the transverse direction too, and your cavity would have to be designed differently because you're not going longitudinal acceleration, you're going transverse.
It looks like the cavity shape should just support a transverse mode just by accident.
Yeah, so there's a whole part of cavity design too that we can talk about which are the modes, the longitudinal transverse modes. But just to give you orders of magnitude, even if you could do that, right, this is above the maximum. And if you want 27 kilometers, you need 8.33 Tesla. So now you're an order of magnitude beyond anything you can do with an electric field.
You don't need to just use one, you can use both, and then you need 1 fewer Tesla for your magnets, which is significant, I guess.
It comes down to, I mean, roughly the orders of magnitude. B fields are easier to bend things than electric fields, but we can talk about it more, yeah. Now, let me just finish off with, this is kind of the modern design for all particle accelerators, and we'll talk about what the changes are. The one thing to notice, though, the synchronization condition for the radius says the energy over B has to be synchronized. I can't use a synchrotron ever to go from E equals 0, okay? That means I have to be at B equals 0. And I also need this B to rise linearly as I go with energy. So it's very hard to make a uniform B field that is so weak and rises with the same rate. So synchrotrons never are going to be the whole part of an accelerator change. So for instance, if you look at how the CERN accelerator complex looks like, what you always do is you start with a LINAC. You start with the linear acceleration. And in principle, you also start with an electrostatic generator, like a Cockcroft-Walton or a Van de Graaff generator. So how you get to roughly 7 TeV is at the LHC, you start with the LINAC here, which takes you roughly to 160 MeV. Then you go through a series of synchrotrons. You go through the booster, the proton synchrotron, and the superproton synchrotron. And that'll get you to 2 GeV, 26 GeV, 450 GeV. And then the last synchrotron is the LHC, which takes you from 450 GeV up to 7 TeV. Now you could ask, why do I have many different versions of synchrotrons in the accelerator chain? Why couldn't I just use one LINAC and one of these? Some of it is a historical accident. When you have a synchrotron that gets you up to something, you don't have to do the entire work for theirs. The other thing to think about, which we haven't talked about at all so far, everything I've written so far is an absolute idealization, okay? If you're taking a particle that has some momentum, okay, it needs to enter in, and your magnetic field needs to start there, right? And then your magnetic field needs to increase. So you should think of accelerators also of having some acceptance for where the beam can actually go in and be close to the trajectory you want. So that's why accelerators don't typically have a dynamic range from 0 to 7 TeV. You build this up in a step so that your magnetic field doesn't need to change from 0 to 8 Tesla. You can be 8 Tesla plus or minus a few Tesla, and then the lower ones can be lower magnetic fields. So this is the modern version of all accelerators. Now the question that was asked, which is a very nice one for the synchrotron, was I keep getting this per turn. Now in the real world, there is going to be some E loss term, okay? So that's what we'll start off with. That's actually going to dictate what are the two different versions of accelerators we have. There's two different ones, a LINAC, where I keep stacking RF accelerators, and a synchrotron, where I keep going in a circle, okay? Synchrotrons, because they go in a circle, you accelerate charge.